The fundamental theorem of calculus part 2 states that if f is a continuous function on a closed interval a, b, then the definite integral from a to b of f of x dx is evaluated by capital F of b minus capital F of a, where capital F is any antiderivative of the little f such that f prime equals the little f. The expression f of b minus f of a is denoted as f of x evaluated at a to b. This is known as the evaluation theorem or the net change theorem. To see this, assume that we have the graph of capital F of x, which is the antiderivative of the little f, from a to b. We divide the interval a, b into many intervals, n to be exact. Their functional values are f of a, f of b, where a is x sub 0 and b is x sub n. There are n intervals. A representative I interval goes from xi to xi plus 1 with the corresponding y value f of xi and f of xi plus 1. We then write f of b minus f of a as f of x sub n minus x sub n minus 1 plus f of x sub n minus 1 minus f of x sub n minus 2 plus plus f of x sub I plus 1 minus f of x sub I plus and the last sum is f of x sub 1 minus f of x sub 0, but x sub 0 is a. Notice that these are the sums of all of these steps, x sub 0 to x sub 1, x sub 1 to x sub 2, and so on. We can put this sum in a sigma notation as I go from 0 to n minus 1 of f of xi plus 1 minus f of xi. Thus the difference f of b minus f of a is the sum of f of xi minus f of xi minus 1 if we switch the index going from I equals 1 to n. But if f is continuous and differentiable on the interval xi minus 1 xi, then by the mean value theorem, there exists a c in the interval such that f prime of c equals f of xi minus f of xi minus 1 over xi minus xi minus 1. If we isolate f of xi minus f of xi minus 1, we end up with f prime of c times xi minus xi minus 1, but xi minus xi minus 1 is the width delta x. This is the sum of f of x star times delta x. And at n go to infinity, this sum is the definite integral from a to b f of x dx.